Hi, my name's Jim Green and I'm going to present questions 12 and questions 15 for the 2020 HSC Extension 2 paper. Starting with question 12, what I'm going to do is run through each of the questions by showing you the solution and then talk about some of the common mistakes and errors for each part of the question. So, for example, question 12A, this is the question here. The solution we were working towards was resolving forces vertically in this case, and pretty much working our way through and getting 400 newtons. And the comment I can make on this is that because the comment of the resultant force of 400 was actually given in the question, one thing we were looking for was some working that actually showed that. In the second part, again, the answer was given, and this time resolving horizontally. The net horizontal force, of course, coming down to 53.2 newtons. And I guess, again, in this situation, we were looking for some form of expression that gave 53.2 newtons, as the answer was already given in the question as well. For the part 3, we needed to use the answer from part 2, and in this case, using the force equals mass times acceleration, we could work out an expression for acceleration was the first step, and then following an expression for acceleration, looking for the velocity. And there were a number of ways to work through this question, either integrating and finding the constant, or doing it the way as on the screen, and going straight to the answer 3.192 meters per second. So some common errors for part A. The result was given, and so many of the students got the answer. Therefore, it made it really hard for us to mark if the answer was just given and nothing else to support it. So the working must be correct, and students should get into the habit of writing down all their relevant calculations. Again, with number 2, the result 53.2 was given, and so because it was given, the working must be correct. It was amazing sometimes that some students got the right answer, but when you check their calculation, it didn't come from their calculation. So write an equation with the sum of the horizontal forces, which are equal to F net, and then some students didn't realise that we needed to work out the net force horizontally. With part 3, many students did not connect with part 2, so they didn't see the connection that they needed to use the horizontal component there. So students need to understand that there's no vertical or diagonal movement, that the particle or box was actually moving horizontally. So there was a lot of calculations about non-horizontal movement. And I guess to teachers, we need to ensure that students understand that if the result or the answer is given, then they must provide correct working that will arrive at the given answer. Also, we found that diagrams will help students understand their question and provide more evidence to give support for their result. In general, the question was done well by the majority of students. For part B, just to refresh your memory on the question, it was a projectile motion question, a little bit different to normal in that it was given in vector form. So the acceleration was given as the vector 0, negative g, not asked to prove it. Show that the position vector, so combining a bit of mechanics with our vector notation, and there were some comments here that were pertinent to, I guess, what the teaching of this could do. So the solution, you'll note, starts with acceleration as given, 0, negative g, finding the velocity vector, and finding when t is 0, the velocity was equal to u cos u sine. And then from there, we could find the velocity vector once the constants were added in, and then finding the displacement vector by integrating once again. And finishing off by finding the constants C3 and C4 both equal to 0 to find the given result. The Cartesian equation in part 2 was found difficult by some for a number of reasons. I think it was the fractions and the powers of the x and the u that caused most problems. So finding t initially, substituting t in to the expression for y to eliminate the parameter t time, we get an expression that can be simplified. And because the expression was given that we're looking for, it could have been a nice transition from the third line to the fifth line. However, a lot of mistakes were made and it required the knowledge that sec squared was 1 plus tan squared. And the last part, part 3, there was a given condition. I guess the biggest thing to note with this particular question was that the handling of the inequality was poor. From part 2, we have a quadratic expression in tan theta, and because we're after theta, then we need to solve the quadratic for tan theta. And if we look at the discriminant, whenever we're talking about distinct and real roots, we should automatically think discriminant. And the discriminant after substituting x equals r came out to be this expression, which was quite cumbersome, but remembering that we're only trying to show that this expression for the discriminant is positive and therefore revert back to u squared is greater than gr, we can show that u to the 4 is greater than g squared r squared, which then indicates that we have a discriminant which is greater than 0. And if the discriminant is greater than 0, then tan theta has 2 distinct values for theta, and so for tan theta, and so and theta as tan theta is increasing. Some common errors with this particular question. With part 1, a good number of students simply quoted the result they'd learned in class. And without doing any of the following, they didn't start with the acceleration, they didn't find velocity, they showed constants rarely, and they really didn't show or know where they were going with the question. Those are the students that basically learn the result and just said it is what it is. With part 2, the result was given, so to obtain the marks correctly without work error was important. And the fractions and the negative signs did cause some problems for students. Some students also lost variables and powers in the simplification process, so be careful. Students should show sufficient working with no leaps of faith, as they say. And part 3, the discriminant was key to getting the result. Many students substituted into the discriminant and then simplified, but then couldn't establish the inequality clearly. And I emphasise the clearly. Teachers, if a question is worth 3 marks, then a substantial amount of understanding must be demonstrated. Students need to be meticulous when simplifying expressions and not lose the variables or the powers. I guess we could ask them to always go back and check and make sure. Many students argued poorly to establish the inequality from the discriminant. This question was done well by the majority of students. And if you take a look at question 12 overall, it was pretty much all about mechanics. And the first was out of 6 and the second was out of 8. So therefore we have 14 out of 100 on question 12, which is a good amount of mechanics. Question 15, on the other hand, expectedly, much harder. And on our new topic of proof, and in the set of integers, this is the question. We found that if k plus 1 is divisible by 3, then k cubed plus 1 is divisible by 3. To prove the proposition P, and I emphasise that this is the proposition P because it comes up later and people did not refer to it, we simply suppose that k plus 1 is divisible by 3. In other words, k plus 1 is 3 times a multiple of some integer. And we can expand using the sum of 2 cubes to get k cubed plus 1 is k plus 1 times k squared minus k plus 1. And we know k plus 1 is a multiple of 3, so therefore we're done. Unfortunately, we found a lot of students that would expand this out and collect terms, or they would expand k cubed plus 1 out and collect terms and lose the correct coefficients. So this is probably the easiest way to go through it, but look, I can't say many people did this. It was more doing the k cubed plus 1. So expanding 3j minus 1 out, cubing it, and then collecting like terms and showing that 3 was a factor. For part 2, a straight definition, what's the contrapositive of p? If k cubed plus 1 is not divisible by 3, then k plus 1 is not divisible by 3. This was simply knowing a definition for 1 mark. For part 3, write down the converse of the proposition and state with reasons whether this converse is true or false. I guess the most problematic part of this question. The proposition of P, not the proposition of the contrapositive. So in essence, some students went back to the part 2 and found the converse of part 2 mistakenly. But what we're after is that the converse is of the proposition P. If k cubed plus 1 is divisible by 3, then k plus 1 is divisible by 3 as well. So this statement is true, and we need to support it with some evidence. And I know this solution is very brief, and there are many solutions I saw which were quite convoluted, and a lot of solutions that ended in it must be true. A very popular word was must or should be without proper proof. Since k must be of the form 3j plus 1 or 3j minus 1 or variations of this, could be 3j plus 1, 3j plus 2, we can show that k cubed plus 1 is equal to 27j cubed plus 1, or 3j plus 1 cubed plus 1 expands out and gives a multiple of a cube plus 2, and the last one here, it's going to have a minus 1 plus 1, so therefore it's the only one that actually gives a divisibility by 3, but that's sufficient. If we use proof by contradiction, supposing k cubed plus 1 is divisible by 3, but k plus 1 is not divisible by 3, therefore k squared minus k plus 1 is divisible by 3, and so we can rearrange to get k plus 1 squared minus 3k is divisible by 3, and hence k plus 1 is divisible by 3. But this is a contradiction, and so therefore it's true. Some students expanded. Now, common problems with this was some students expanded the difference of two cubes and finished with the incorrect coefficients, as I said. In part 2, not difficult if you know your definitions. There's not much more I can say about that one. And part 3, students often got stuck and the word must gave the correct solution. There were some very creative techniques, but often these needed more explanation as they were very brief, and some came from outside the content of the syllabus. Advice to teachers would be, when a question asked to answer with reason, then some explanation should be given. Some students referred to truth tables and proceeded to state the result to 3 without sufficient explanation. More practice on testing cases should be done. And this question was found difficult by the majority of the students. Moving on to part B, about vectors. Interestingly enough, this question here shouldn't have been a problem, but it did cause problems with notations. From the diagram, we can see that OA plus AC plus CB is equivalent to OB. And by substituting in with the variables, the vectors A and B, we can see that, and we know that CB was given, it's M over N times AC. We can substitute in, and we can rearrange by factoring out AC, the vector AC, and then rearranging, we get the value of N over M plus N, B minus A. Done very well to a large extent. Moving on to part 2, there were many students that simply started with the result and went around in circles and came back to the result. I guess in this case, we know that OC is equal to OA plus AC. we know OA is A and AC from part 1 we've already found. So substituting in and rearranging, some creative rearranging gave the result that was required. Now in the last question part 3, you're asked to show that OT is 2/3 vector R plus 1/3 vector P. And in this case, it was a matter of finding vector equations for the lines and solving them simultaneously was the most efficient and probably the most effective technique used, although not the only method available. So OS was OR plus SR, which is vector R plus a half vector P. Pretty straightforward. Equations of the line OS is X, vector X, and that's equal to vector R plus a half vector P times some scalar quantity lambda. And PR is also X, vector X, which is P plus R minus P times some scalar mu. By solving these simultaneously and equating the coefficients, we can see that a half lambda is 1 minus mu, and that lambda equals mu, and so we get lambda is the scalar quantity 2/3. And so by substituting in for OT, we find that it's 2/3 R plus a half P, which expands out to give the required result. And as I said, this was probably the most effective way that students who used this method generally got the full 3 marks. Part 4 says to use parts 2 and 3 or otherwise to show that T is a point that divides the interval PR in the ratio 2:1. By part 2, the point which divides PR in the ratio 2:1 is given as that result, but this is not OT, but this is OT, sorry. Therefore, T divides OP in the ratio 2:1. Now, some comments on this include there was an overall poor use of vector notation. Whether students were getting to the end and rushing, notation was very poor. Few could use line equations to solve the problem given, although not part of the course. Some students used internal division theory, and again, more explanation would have been beneficial. Some students used the result to show the result. Yep, many did not see a connection with part 1. For part 3, best answers use vector equations as a set of the lines and solve simultaneously. Many simply substituted into the result from part 2 without any explanation. And students needed to ensure that previous results were applied accurately. Many had components reversed. When the result is achieved, check that the result is actually correct. And I guess in our classrooms, we need to encourage students to use notations for vectors correctly. Students should always look for connections between parts of each question. Overall, the question was found difficult by the majority of students. And again, this particular question, number 15, was pretty much half and half proof and vectors. Thank you very much for listening.